So today I would like to focus on uh, different kinds of mixtures, especially mixtures that are really kind of important to us. They're called solutions, suspensions, and colloids. And there's a lot of really neat examples of each of these. All right, so we're in question number 12. Water mixtures are classified according to the size of the particles dispersed in the water. What are the three classes called, and what distinguishes one from the other? Number one, suspension. Here you have very large, easily seen particles. They will disperse when mixed, but eventually gravity wins out and they begin to settle out. So if you've ever played around with a watery mixture where there's a lot of particles and then eventually it clears up and then you see the sand or the grit down in the bottom, that is a suspension. So, pond water at first may be very muddy, but then you just let it settle out and you'll see different layers of different types of large particles. A colloid are very tiny particles that cannot be seen, but they may make water look cloudy or even opaque. So these are tinier than suspension particles, but much larger than solution particles. So think of suspensions as Papa Bear. This would be Mama Bear type particles. They are big enough to be seen, but not so big that gravity will pull them down. They won't ever settle out. Milk is a good example. Now, what's really interesting about milk is that when your great grandparents were around, if they got milk, they needed to shake the milk. Why? Because milk was a suspension at that time. What that means is that the milk particles would be so large that they would eventually settle out. So if you did not shake your milk, then that first few drinks of it would be really watery and yucky. And the last little bit of it would be really thick. So you had to shake it up in order to create that suspension. Now, back in the 1950s, the homogenization process was invented. And in it, they took these big giant milk particles that came from a cow and they broke them down in order to make milk into a colloid. You no longer have to shake the milk because the milk particles will always be suspended. They're now small enough to be carried around along with the water, and they'll never settle out like it used to back before it was homogenized. So what's really funny is you still will see kids in the cafeteria shaking their milk. Why? Because their parents shook the milk. Why? Because their grandparents shook their milk. Why? Because their great grandparents shook their milk. And if they didn't, then milk would taste really yucky. So there you can see the big giant globules of milk. A solution are particles that are so small and so evenly distributed that they appear to be clear. It looks like it's just water. For example, salt water is an example of a solution. Sugar water would be an example of solution. Drinking water is an example. Remember, the drinking water is going to have all sorts of contaminations in it. So if you can see straight through it and you don't see teeny tiny little particles, it looks like water or maybe even colored water, that is a solution. Here is whole milk at 1,000 times magnification. And 400 times, you can no longer see some of the smaller particles. You can still see some of the bigger particles. Here's non-fat milk. A lot of the larger particles are broken down into smaller ones. So how can you tell a colloid from a solution? The Tyndall effect. Now, the Tyndall effect is very interesting. Have you ever been in your bedroom and the sun comes through the window and you can see like streaks of sunlight? You can see that because there are enough dust particles in your room that allows you to be able to see the light. Because what the dust particles are doing is they are reflecting the light back in your eye. Maybe you've seen it out there in the weather and you see a streak of light coming down. Well, that's probably because there's a lot of water droplets in the air, maybe some dust particles in the air that allows you to see it. The Tyndall effect is what we call being able to see light because there are particles in the atmosphere, or in our case, in water, that are large enough to be able to reflect the light back at us. So, as you can see here, this solution may have particles in it, but they're too small to reflect the light, while this one has particles that are large enough. This is how you can distinguish a solution from a colloid, because sometimes colloids may look perfectly clear. So, in review, you shine a flashlight through 3 bottles. In the first bottle, the light goes in, you don't see it, and then comes out the other direction, on the other side. In the second bottle, you see the light going through. And in the final bottle, sometimes the light is completely blocked. Sometimes you can see it for a little while, but you will see large particles. That is a suspension. So a solution, you can't see the light. A colloid, you can see the light going through. A suspension typically will block out the light. So, a true solution, no light. A colloid, you can see the light. A suspension, it'll either block it or you will be able to see these large particles floating there. Can you see the Tyndall effect? There is the Tyndall effect. Both of these are examples of colloids. Colloids. All right, what about this one? What is that? That's right, colloid. No light, solution. Colloid. Examples: sugar water, drinking water, salt water. Colloid would be milk. Suspension would be muddy water. And you're probably thinking, well, why isn't milk a suspension since it's opaque? Yeah. Does milk ever settle out anymore? No. Hey, how about another example? What if we were to put some chocolate mix? I'm not sure that's spelled right. Chocolate mix in the milk. Does the mix settle out? Does the chocolate? Yeah, it does. I remember when I used to have chocolate milk, I would drink the milk real quickly so that I could find all that chocolate down on the bottom, and then I would take a spoon or even my fingers and spoon it out. By the fact that you have some chocolate settling out, that tells you that it is a suspension. A suspension. All right, so let's review. Light, Tyndall, no Tyndall effect. Light goes in, comes out the other side. A colloid, Tyndall effect. A suspension typically will completely block out the light. You may see a little bit of light eking through. Okay? But basically, Tyndall effect is used to tell the difference between a colloid and a solution. Typically, a suspension, you can easily tell. All right. What do you think? Element, compound, or mixture? Let me help you think it through. A, barium chloride. Notice that I gave you two element names. If you have two element names like that and a formula, it is a compound. Two element names. Compound. Now, for the rest of these, you just have to kind of think them through. If you can't, if you don't know for sure, then look them up. For example, Google air, and air will tell you that it is a mixture of oxygen and nitrogen with some smaller amounts of other gases. So this is a mixture. How about pepperoni pizza? Oh, air, is it a hetero or homo? I would say it's homo because usually the oxygen and the nitrogen is evenly distributed. How about pepperoni pizza? Well, yeah, I can see the bread, I can see the sauce, I can see the cheese, I can see the pepperonis. So this is a mixture, and it is hetero because you can tell the different parts. Table salt. Now, this one is a little more difficult to understand. Let me just tell you this. I can buy from a scientific supply company a pound of sodium chloride for about $56. Or I can buy a pound of table salt for about 56 cents from Walmart. What's the difference? Well, from the scientific supply company, it is going to be 99.99999% sodium chloride. For all intents and purposes, it is a compound. But from the table salt from Walmart, they don't care too much about it being pure sodium chloride. It is mostly sodium chloride with some other white crystals there that are not going to hurt you if you were to consume them. So this is a mixture, and typically you can't tell the one white crystal from another. So I would say it's homogeneous. How about salt water? Well, it is a mixture because it's made of water and salt. Can you tell where the salt is? Can you tell where the water? Maybe if you add a ton of salt, you can tell that there's salt down on the bottom. But if you just add a spoonful of salt, no, you can't tell. So it's homo. Strontium is an element. It's on your periodic table. And oxygen is an element. It's on your periodic table. So, one more time. You have a bunch of green atoms and a bunch of orange atoms. What do you think it is? Well, they're not combined together. They're two different kinds of atoms, so it must be a mixture. Looks like you have a combination of blue and red, and they are combined together, but it's still a combination. So this is still a mixture. Now you have what appears to be a red atom with two white atoms attached to it. I hope by now you're recognizing that that's water. So notice that every one of those particles is one red and two whites. That would make it a compound. All right, so here you have the same type of atom. It's all yellows. Even though they're combined together in couplets, it's still all yellows. So that would be an element. All purples. Element. How about this one? Purples and some gray with blue, three blues, and some yellows. That would be what looks like a mixture of elements. a mixture of compounds, containing compounds. So this would be a mixture. How about this? Same kind of particle, always one gray, three whites. What would this be? A compound. Which one do you think is heterogeneous? Well, yeah, I can kind of tell. We have different parts here. That would be heterogeneous. How about that? Yeah, heterogeneous. These look like they're more uniformly throughout. So, not sure what my colleague who created this was thinking. I think this is the one that is definitely heterogeneous. All right, hope you enjoyed that.